You know, when cancer spreads, it often finds a new home in our bones, and that creates one of the toughest, most painful challenges in all of modern medicine. But what if we could fight it differently? Not with a flood of powerful drugs, but with an army of microscopic, precision-guided healers. Let's dive into how this tiny medicine is taking on a giant challenge.
So this is the big question, right? Why is this specific problem so incredibly difficult? Well, the answer really lies in the unique, complex environment of our bones and, honestly, the limits of the weapons we currently have in our arsenal against cancer.
Okay, so before we get to the really cool solutions, we've got to wrap our heads around the problem. And make no mistake, when it comes to cancer, bone is one of its toughest strongholds.
Now, here's something you might not realize. This isn't what we typically call bone cancer. This is cancer that started somewhere else, say in the breast or prostate, and then it traveled or metastasized to the bone. And that's often the most dangerous stage of the disease because the bone gives these cancer cells the perfect place to hide and grow.
For decades, our main weapon has been chemotherapy, and you can really think of it as a shotgun blast. It's powerful, for sure, but it's not precise at all. It takes out cancer cells, but it also causes so much collateral damage to healthy cells, and that's what leads to those awful side effects. The dream, the goal, has always been to create a guided missile, a therapy that can seek out and destroy only the cancer, leaving all the healthy tissue alone. And this is where nanotechnology comes into the picture. Scientists are literally engineering tiny vehicles, way smaller than a single cell, to carry out this exact mission. So let's meet the hero of our story. Okay, so this is a lipid nanoparticle. At its heart, it's just an unbelievably small sphere made of fats, or lipids, basically the same stuff that makes up our own cell membranes. The easiest way to think of it is as a tiny biological shipping container built to carry a powerful cargo safely through the chaos of our bloodstream. So let's take a look under the hood here. This diagram shows us a liposome, which is a type of nanoparticle. You see that outer wall? It's made of these fatty molecules, and they create this really secure little space on the inside. What's so clever about this design is that it can carry water-based drugs in the middle and fat-based drugs tucked into the wall itself. It's like a delivery truck that has both a main compartment and a refrigerated section. It's incredibly versatile.
So what makes these little trucks such a massive game changer? Well, it all boils down to a few huge advantages. First, they're biocompatible, which means our immune system pretty much ignores them. They also act like a protective shield for the drug, making sure it doesn't get destroyed on its journey. But the most important thing, the real magic, is that they can be engineered with that guided missile precision we've been talking about to hunt down a very specific target.
But wait, it gets even better. Scientists aren't just building one kind of nanoparticle. No way. They've developed this entire toolbox of tricks and strategies to make them smarter, faster, and even more targeted. This image does a great job of showing all the different tools they have. I know it looks a little complicated, but don't worry. We're going to break down 3 of the absolute coolest strategies that scientists are using right now to turn these things into sophisticated cancer-fighting machines. All right, the first strategy is all about navigation. I mean, how do you tell this little nanoparticle where in the whole body it needs to go? Simple, you give it a GPS. Scientists can do this using molecules called bisphosphonates. Now, these molecules just have this natural, really strong attraction to bone. So by sticking them onto the outside of the nanoparticle, it's literally like putting a zip code for bone on the package. When it's in the body, it just circulates around until it finds and latches on to bone tissue, delivering its drug cargo right where it needs to go. It's brilliant. Okay, this next strategy is just so elegant. Instead of trying to build a delivery vehicle from scratch, why not just borrow one that nature has already spent millions of years perfecting? So, on the left, we've got the man-made liposomes we've been talking about, but on the right, that's something called an exosome. These are nature's own nanoparticles. Our cells make them all the time to send messages and materials to each other. You can think of them as the body's internal high-priority mail service. And because our own bodies make these exosomes, they are absolute masters of stealth and delivery. Their surfaces are covered in all these proteins that act like a specific key, letting them unlock and get inside certain cells with amazing precision. They just know how to navigate our internal systems perfectly. All right, so you've guided your nanoparticle to the tumor. Fantastic. But now you have a new problem. How do you make sure it stays there long enough to actually work, instead of just getting washed away by blood flow? The solution? You give it an anchor. This is so cool. As you can see on the left, scientists basically mix the nanoparticles into a liquid hydrogel. They then inject this whole mixture right at the tumor site. The gel then firms up, kind of like Jell-O setting in the fridge, and it creates this scaffold that physically traps the nanoparticles right where they need to be. This anchor makes sure they stick around, letting them release their medicine slowly and steadily for days, or even weeks.
A molecular GPS, nature's own delivery system, a hydrogel anchor. I know, it all sounds a little like science fiction. Which brings us to the big question, right? If this stuff is so amazing, why isn't it in every single hospital today?
Well, the science itself is definitely solid. I mean, look at this table. It shows really clear examples from lab studies where nanoparticles took existing drugs and just made them way, way better. They're getting sustained release, which could mean fewer doses for patients. They're helping drugs get into bone where they couldn't before. The proof of concept is absolutely there. The science works.
But, and it's a big but, getting from a lab to a life-saving treatment is a marathon, not a sprint. Just try to imagine the challenge. You have to manufacture billions upon billions of these tiny particles, and every single one has to be perfect. It's a massive engineering problem. It's expensive. And on top of all that, you have to go through the years-long, incredibly strict regulatory process for a totally new kind of medicine. It takes a ton of work.
Even with all those challenges, the potential here is it's too big to ignore. This kind of research represents a true fundamental shift in how we even think about medicine. When you boil it all down, what we're witnessing is the move from the shotgun blast era to the guided missile era. It's a shift away from just flooding our entire bodies with toxic chemicals and hoping for the best, and moving towards sending in tiny, programmed healers that go only where we tell them to go.
This whole thing isn't just about treating one type of cancer. It's really a glimpse into the future of medicine itself. A future where our treatments aren't just powerful, but they're also smart, they're precise, and they're personalized. And it just leaves you wondering, what other diseases could we finally conquer with an army of these tiny, programmed healers?